we'll go ahead and get started. This is a pretty short presentation, so really, we're looking at about 30 minutes probably with Q&A. So we should be able to fit in all of that we want with questions and whatnot. Today we're going to be talking about UL 9540A. This is fire safety testing for energy storage systems, and really what the importance and what Simplify specifically has gone through. I just want to emphasize, I'm probably not a complete expert in this field just yet. This is new for a lot of us. It's definitely something that we are still learning a lot about, and still kind of going through the motions on and what the implications are of it, how it can be used. Just actually sat through a meeting yesterday talking about how it can basically satisfy some needs for local inspection and hopefully speed up the process. So again, I might not be able to answer every question as it's a little new to me as well, but I'll do my best and always, as always, send follow-up. All right. If you have any questions throughout the presentation, scroll up to that control bar. Once you get to that control bar, you'll be able to hit the Q&A, type in any questions you have there, and we'll get to them at the end. All right, let's jump right in. So let's start with what is UL 9540A fire safety testing. So UL 9540A safety testing is really just a series of progressively larger tests involving forced thermal runaway. And I can't stress enough, this is forced thermal runaway. And this has a lot to do with the test is kind of seeing where that threshold lies on when the battery and the cells and the system will go into that thermal runaway. Beginning at the cell level, and it progresses to the module level, and then the unit level and installation level. And what I mean by this is kind of looking at cells, the battery as itself, an ESS type solution, an energy storage solution, or even just a cabineted solution, and then a system altogether. There is no certification listing for UL 9540A. This is still just a test protocol, but it's kind of, then again, this is what I'm talking about with these implications of how this can be used to basically help out. So it helps manufacturers and system integrators meet the IFC 2018, the upcoming codes, and NFPA 855 by evaluating effects of thermal events or thermal runaway, the potential for fire propagation and or explosion. So basically what this is it's a way for us to kind of define, this is our specific chemistry, this is our specific battery, this is our specific system. What does this mean in terms of fire safety? And what does it mean in terms of propagation and what you might need as far as safety requirements, spacing requirements, and all sorts of stuff. So this can really kind of lay the groundwork for each battery being a little different and definitely each chemistry being different. It evaluates and determines the inherent safety of the battery chemistry itself, the manufacturing design and materials, as well as various safety mitigation strategies that may be employed. So basically just what I just said, again, looking at maybe you've got one battery over here that uses a different chemistry, or it's just a different design that requires built-in fire extinguisher. I think we all know that one that just recently had that added to it. So that's, a different safety protocol than, for instance, our batteries are going to require based on these tests that kind of validate the claims that we've always made. We're really just kind of putting it in a hard test here to show the data itself. On the right here, you see kind of a flow chart. You can see the cell level testing, reported information there being the cell design, the thermal runaway methodology, cell surface temperature, at gas venting, at thermal runaway, gas composition, and understanding what is actually in that off gas in those situations, performance, the thermal runaway. Basically, this is what the test needs. So thermal runaway cannot be induced in the cell. Then flammable gas concentrations in excess of 25% or lower flammability limit of the cell vent gas as determined in the accordance, and I won't bore you with all the code stuff here, are not produced. So basically that's kind of, I know it's a lot of mumbo jumbo there, but basically saying if the cell level can exceed or can basically show performance there, no further tests required. It's just not going to happen with lithium batteries, as we can basically force most batteries into some sort of gas or fire, but you really have to force it for some batteries versus others, with basically looking at parameters that would never exist in a real installation, but it's still something we can force. Similar on the module level, we're just testing for heat release rate, gas generation and composition, external flaming and flying debris hazards. I won't bore you with all of this. BESS, you'll see there, battery energy storage system design. Heat release rate, again, this is for unit level testing, gas generation and composition, deflagration and flying debris, deflagration being something we'll talk about a little bit later, but basically, understanding those, how we can deal with propagating fire, and installation level testing. So again, I think I won't dive too deep through this flow chart, but definitely take a look at it. If you have a copy of this, which it'll go out after the presentation in a couple days, I would take a look at it. It kind of gives you a bit more of a breakdown of exactly the flow of the test, but we'll go through that as well, at least in terms of our testing. So results from the UL 9540 test method address. So basically, why does it matter? It mandates BESS, so again, battery energy storage systems, installation instructions that ensure safe operation. So again, this will be different between different systems, different chemistries, different manufacturers even. Informs installation ventilation requirements. So I'm going to keep harping on it, but again, different. That's what this is. It's showing, hey, this is this battery. It requires more ventilation, or this one requires less ventilation. Proves effectiveness of thermal runaway propagation, protection inherent to the battery or the system, if required. Informs strategies and tactics that may need to be incorporated to eliminate fire and explosion risk. So again, all this stuff is really all about safety. It's how we understand, this is the level of fire propagation necessary based on this test. So now we know what needs to be put in place, how these tactics can eliminate these risks, and also allows for the inspectors to understand, hey, this is this specific test based on this battery. This one might need more than the other. So we need to make sure we're checking for those requirements. It informs the system safety characteristics and sets a bar for performance comparison, encourages safety within the industry as a whole. All right, let's jump into testing breakdown. So this testing breakdown is specific to what we saw. So that's kind of where I'm going to jump through this. And it'll be very, very specific to our testing through UL. So this is our module level test. So the module level testing of the Simplify 3.8 battery, basically 7 cells within the battery heated with thermal wraps. The cells in the battery module were subjected to extreme levels of heat to force a state of thermal runaway, which I'm proud to say took quite a bit in our battery to actually force, versus some of the other lithium batteries. These are quick, easy. You force them into thermal runaway by just getting a little bit of heat on them. Ours really needed to be forced, and we need to kind of work through that and make sure that it was forced into some sort of thermal event. The cells and battery module were subjected to extreme levels of heat, again, to force the state of thermal runaway. Successfully completed testing for the Phi 3.8 kilowatt hour battery, their standard battery rate here, modules and its component LFP cells that are in the battery itself. So this is on both the battery level and the cell level. Test results concluded that the cells and battery modules did not produce fire or cause fire propagation. So that's great for us, even in this case of forcing those cells into thermal runaway. Again, it's a tough thing to force in these cells. the battery still did not produce fire or cause fire propagation. It's a huge selling point and really a jumping off point when you're talking to customers, and they might be looking at a battery that did not hold up so well in the 9540A testing. Maybe it's using cobalt-based chemistry or other types of chemistry. It's really important to kind of talk about this, as it's a big factor when it's in your home, when it's in your business. You really want to look for these safety measures and make sure that you aren't putting something that could cause potential fire and damage in your home, business, wherever it may be. Now we move on to the internal testing. So this is unit level testing of the boss cabinet. So the boss cabinet here shown is the 12 battery, excuse me, boss cabinet. And I see some questions coming in, just make sure everything's good. Okay, perfect. So this is the 12 battery boss cabinet. And basically this is the unit we're going to test for. I believe, if I'm correct, it's this specific battery right here that is put, so single battery, same way it was heated before, the 7 cells, same test protocol as the module level. So basically forcing thermal runaway here to see how the system as a whole reacts. And what that means is, this is, we see it on a battery level, right? We want to understand what happens if thermal runaway occurs on a battery level. But we also want to see, and maybe it's a little bit redundant at this point for us, as the battery didn't cause that kind of fire, but we want to see if one battery does go, how the other batteries around it will react in this enclosure. You'll notice some scuffs here. That's just the one we sent, I believe, was a unit we weren't going to use anyway, as it had a blemish on it. So that's why that scuff's there. It's nothing to do with the test or anything like that. So the initiating 3.8 48 volt battery was located in lower middle position. Yep. So right here, that's kind of the battery we're looking at. Various thermocouples and instruments for testing within and outside of the cabinet, basically used to monitor these monitored for heat rise within the cabinet and transfer to adjacent batteries, cabinets, and surface exterior to system. Why is this so important? Really understanding kind of a chain reaction in some other types of batteries. Lithium batteries, lithium iron phosphate holds that really strong characteristic where it does not have so much of this risk. But there's other types of lithium batteries where if one battery catches fire and it's in a case, or maybe it's built around multiple units, how does that react? And how does that kind of cause some sort of chain reaction, which can be even more threatening to the safety of the system? So here's a little look into the actual testing. You can see here kind of the spatial overview here. We can actually see the distance here between the wall, and actually see the 12 feet. That actually makes sense here with these two cabinets. This is the initiating cabinet. So this is where the cells are basically forcing the thermal runaway. And basically the reasoning for this is, again, even bigger, broader picture, understanding fire propagation here, what's going to be happen here and here, what happens to the wall even. Those are kind of important things that we need to look at. And that's really, it helps us a lot there, where we can say, this is within this cabinet, what happens and what happens here and here. So that's just kind of a rundown of the test, giving a very rough idea of the test. We don't have even batteries really showing issues within the cabinet. So of course these cabinets aren't going to show any temperatures. And we'll talk about at the wall exactly what that temperature was as well, coming up here in a little bit. We'll go through the numbers. Just a little bit on the thermal coupling. It's important for us to kind of understand where those sensors are. So again, this is the one that's going to be put into that state of thermal runaway. But here we have the different thermocouples all over the system to really catch the data and understand what's going on. We also have them on the outside This is to make sure that we're catching anything that's going on the outside, as well as at other units within this test. And again, this is all done by UL. This is not something we're doing in-house by any means. This is basically a way for us to validate through them what we have always kind of known regarding our system safety and whatnot. So again, this is performed by UL. So let's look at the unit level testing of the boss cabinet. So you can see initiating unit temperature here. I saw there was a question in the chat about that. So that's kind of where we can see where the actual venting occurs and the actual initiation. Here's where we want to look at basically these kind of different figures here. You can see well over 50 C, almost to 60 C. So results for subject battery were identical to the module level test when forced into thermal runaway, with propagation limited to some cells directly adjacent. So again, that's the cells in the battery itself, not batteries around the cells. No module to module propagation detected. So just to go back, we're talking about not even propagation between this and this, just internal to one single battery. So that's where the safety factor really comes in, is we don't have that issue of this battery catches, now it catches all these batteries. Even when that forced event occurs, it's just within the single battery, no module to module. Minimum fire explosion risk, minimizing deflagration strategies. So that is a big help. I know a lot of projects where we've looked at some really, really high demand deflagration, which is costly and it's expensive, and looking at specific latches that are required for those kind of things. The idea is now we can start to cut things out that are not necessary. Highest temperature of 60 C at adjacent batteries around the initiated battery module. Temperature dropped rapidly after the test was concluded. Temperature rise in adjacent batteries within the test unit were unremarkable, as in there was nothing to be measured beyond just its normal temperature. The back wall, so to go back, sorry, I keep jumping around, that's in reference to this wall here. You can actually see the wall in this diagram, plywood wall. Back wall showed temperatures of 5 degrees Celsius, below the threshold of combustion. This is what we want to see. The safety, if there is an event, lies in the cabinet. If it lies actually in that battery, to be really honest, and not even in the entire battery, just in some of the cells. This is where we have that safety factor, where the wall behind it is really the most important thing to look at during this test, as it has so much to do with what you might experience as a catastrophic damage to a home or anything like that. It all comes down to that. It's what is that wall catching? Is it catching on fire? Is it showing high levels of heat? No, in this case, we are not showing that through these tests, which is great. So why is it important for installers? You understand and communicate with the AHJs on requirements for installation. It's going to be a learning curve. There's no doubt. I mean, everything we do in this industry is always a learning curve when it comes to inspection. So we'll work through that as it gets through it. But it's important to kind of know that sometimes you might need to stand on your own 2 feet and say, well, I know you probably need to see the 9540A inspection. Let me get them to send it to you so that you understand the actual requirements that I know are true. Providing analysis of test reports when required. We've definitely done this already a lot. This is taken off. So we typically can send it straight to the inspector, from my understanding. I don't work a lot in our pre-sales department, but that's my understanding, as I've seen them being sent straight to inspectors when required, or just when asked of. What additional fire protection equipment and shutdown mechanisms may be required for ESS? So basically, these may be needed regardless of chemistry or analysis of the test reported by AHJ. Understand these requirements ahead of time. So unfortunately, while these tests are great, that still might be the requirement. So it's just important to know, but you might have certain situations where there's less requirements based on this testing. Different concerns for different chemistries. Requirements and safety considerations apply to system capacities less than 600 kilowatt hours. So basically we're looking at 3 feet separation distance between groups unless UL 9540A testing allows for reduced spacing. Differing requirements for different chemistries. Again, that's probably the low end of things. UL 9540A informs spatial requirements for UL 9540, which is the actual ESS listing, which we do have on our systems as well. The two do go hand in hand. It's not just a coincidence, obviously, and it will allow to basically inform the spatial requirements when looking at an ESS system under the UL 9540 umbrella listing, and will become a requirement for installations. It already is. I don't know, I'm sure there's a lot of people from different areas on this call, but it's catching on quick. And it's going to become a requirement everywhere. And I just sat through some meetings yesterday with some of the stuff in California, and it's definitely a main topic of conversation to really kind of reiterate both a UL 9540 listing itself, but also how the UL 9540A test protocol goes along with that, and spatial requirements, as well as fire suppression requirements and thermal management, as well as ventilation and exhaust, smoke purge, venting, and deflagration venting. So this all ties together with that all-in-one ESS solution and how it's going to continue to relate to the UL 9540A standard. So we'll wrap up here. Using the highest quality cells, this is kind of just a little ditty about us, and lithium chemistry, Simplify maintains levels of battery safety that goes beyond the baseline of standards. This is really important. We saw great test results here, and it's not just simply the chemistry. It's easy to chalk it all to the chemistry, but it also has a lot to do with manufacturing practices, understanding where things go, where things are. So that's really important that we kind of keep an eye on looking at LFP versus LFP, as well as not just looking at, oh, it's LFP versus cobalt-based lithium chemistry. It is about both the cells and the manufacturing process as well. Even when put into thermal runaway, our batteries continue to show low probability for fire propagation. Again, this is a forced thermal runaway, though. This is not just the norm. This isn't, this is something that really needs to be forced, or a really bad system design, or maybe just pushing the batteries extremely beyond their own bounds. Not only are we able to provide a safe, reliable product, but also cut out various safety systems and points of failure other batteries rely on. Definitely when looking at cobalt-based batteries, we see a lot of that. So I know I ran through that. It's a pretty short presentation as we're all kind of learning still. I'm gonna pop open the Q&A. Again, I'm gonna warn, I might not know the answers to every question, so I will do my absolute best though to get through it. Can you define extreme level of heat with a number? Good question. It's in the test report itself, which I believe we can always pass out copies, at least to the AHJs, I know for sure. So I would need to kind of look through that, but we can always get those numbers if it's required, but I'm not sure just off the top of my head, sadly. What is the recommended fire suppression method for lithium ion battery chemistries? How well might this fire suppression method mitigate thermal runaway? Good question. Again, it depends on actually, it doesn't really depend as so much on the battery chemistry. If we're just talking about what to use, my understanding is like a fire extinguisher is probably the best suppression. Obviously, it's an electrical fire. I don't want to throw water on the thing. So we want to look at suppression like that. From what I'm seeing on the really high level, these are the high risk lithium batteries, is fire extinguishing. So that whether that's built in, as we've seen in a few batteries recently, or whether it's required externally or close to the system. All right, well, we don't have any other questions come through, but I am available for any other questions that you do have that you kind of, hit your head after the presentation's over. You can always email me at training@simplifypower.com. If you have any suggestions how to make this better, more relatable, this is a new presentation. We're always open to anything as far as recommendations go. All right, thanks everyone so much. I hope you have a lovely day.